So welcome to this live session for this course on numerical methods and simulation techniques for scientists and engineers. So we have seen a number of techniques, and of course these techniques were only shown on a theoretical platform, that is the formula associated with this and the principles behind this, and we have also done elaborate discussion on the error calculation and how error propagates. So by and large, this gives you a sort of a basis or a foundation in using numerical methods for your research. And I was happy to know last time when it ran, the number of questions and people who have attended, they have taken up numerical studies, and at least two of them are doing molecular dynamics simulation of certain classical systems. In fact, this was the idea that it's not usually it's only numerical methods that one talks about and gives you an overview of various methods that are there in solving equations and so on. But here we went ahead of that and discussed some simulation techniques um, that are involved. I mean, two of the simulation techniques. There are many simulation techniques that are there, but two of them which are commonly used in science and engineering. One is called the Monte Carlo, the other is molecular dynamics. And I believe that sort of gives a complete overview of numerical techniques that can be used in order to attend problems of different kind. And we have gone and attended problems in, say for example, chemical engineering, say for example, civil engineering, and physics and chemistry and so on. These would be, essential for you to have a flavor of what are the different things that people do using numerical methods. So numerical methods actually has all the different techniques for solving equations, for doing integrations, for doing differentiations, for solving, say for example, the differential equations in an iterative way, and also that there are various things related to interpolation. So when you have a large amount of data and you know what function does it fit best to, you can do a Lagrange's or a Newton's interpolation, and these interpolations are very important in making predictions about about the data that you have. And very importantly, this connects to the machine learning that one is talking about. So it's not only about predicting the behavior from a given set of data, but also making further estimates of what could give rise to, or what could it be in terms of future predictions. So these course, I believe, that had given flavor on a number of important different topics which are required for one to attend problems at undergraduate levels, graduate levels, and also at the research levels. So that way it should be a course that you would be looking for now, and hopefully in the future as well. Any question? Anything that you want to ask? I see 10 people watching now. Good morning, Abhishek. Please ask me if there's any doubt or anything that I can help you with. Meta heuristic techniques, and I have no idea. I have no clue on what's a meta heuristic techniques, or can you be a little more specific what you're asking? What is in connection to? Yeah, so let me take Rakhi's question. It says that tell about the errors while doing numerical simulation. This is a very important part in the sense that if you do not have rather a good estimation of the error, then this error will keep propagating and will probably take over the actual values of the data. So it is very important to do an error estimation of at each step of the iteration in every simulation, and try to minimize it to the extent possible. Such as if you are doing sort of say trying to solve a differential equation, and then the iterative errors that come, they come because of various things. One of them is the round of error, and this round of error you can try to minimize it, and such that it doesn't grow in every iteration that it goes through, the simulation goes through. And if it does, then it will be difficult to control it, and it might actually take over the actual values of the data. So that is something that you should try to take a control on. So simulation, the error measurements or error estimates of your data is very, very important. Okay. Genetic programming, if you're asking, I don't know much about genetic programming and what they do. I'll have to really think about what are the real problems in. I mean, the genome sequence, etc. These are mostly, I mean, that's also part of the machine learning. But how exactly our numerical methods course is used for genomic or genetic engineering, I'm not too familiar with. Good morning to rest of you, Chinmay Tripathi and Suman Yadav. Good morning. And more questions? So I hope the course has been useful to you. What's a good error convergence criteria used in softwares? Double precision is of course one thing that takes care of the round of error. Okay, so yes, one of the things that is there is called the using double precision, that will take care of the round of error. But that's not the only error. Okay, I mean, round of error is not the only error, as we have discussed. There are other kinds of errors also. And I believe the softwares do an optimization between the speed as well as the convergence. Okay, speed of convergence, that is. So there's an optimization that is required. If you look at the the error calculation in say for example the Newton-Raphson method, you see that there is a competition between two terms. One grows, one dies. So such an optimization is needed. So the softwares, most of the softwares use this optimization. Yes, deep learning and machine learning are really used in, I mean, but they are based on the traditional numerical methods, okay? And then after that, they require a lot of input. Say, for example, I mean, you want to know the carbon emission of a particular car company, automobile company, which is very, very important these days. And you have the data over the last, say, for example, 5 years. And so the carbon emission versus time in various cities, in various states, etc. So it is from there you want to make a prediction about the design that the automobile company wants to do in order to have a check on these carbon emissions. Okay. So these are really these are so all these things for the deep learning or the machine learning, artificial intelligence, their basis lies in the numerical methods. So Raki, good question that how do we actually go through the equipment errors in numerical simulation? So these are, I would say that when you do a numerical simulation, then you don't go to the lab and do that experiment. In fact, some of the experiments, as I have said while speaking in the class, that some of the experiments are too expensive or they're too dangerous. And because of that, you don't want to take the risk of doing it in the lab. It's either hazardous, could be poisonous, or could be, there could be some explosions which you don't want to have risk of human lives. So you do a numerical simulation of that. So really the equipment errors do not enter into the numerical simulations. But yes, when you do an error calculation, and you take the least count of for a given suppose you are measuring a line, measuring the length of the line, and then if the length is say 90 centimeters, and you can say that your 1 millimeter is the smallest scale length scale of the measuring device that you want to measure with. So you use 1 millimeter as your least count. So that way the least count enters of the equipment enters into your numerical simulation as well. Most of the time we don't worry about the equipment errors, but sometimes we need to worry about, and when we worry about it, when we actually worry about the least count. Say for example a multimeter, whether it's 1 millivolt as the the least count, or 1 microvolt or whatever that is, that needs to be taken into account. Yes. Arsha, Naushad, good question. I mean, when you solve ODE and PD using softwares like MATLAB, it is fairly accurate. I would say that no, you don't need error correction. In fact, they use all the methods that we have learned during the course. Those are embedded into it, and an error optimization is also embedded into it. So after that, you don't require anything. But interpretation of data may require you to do some more work. Yes, the supercomputing facility at IITG you can take benefit from, and you have to write to the. There are people who are in charge of the supercomputing facility. I believe that's called Communication and Computing Center. You have to write to the head explaining your project and how you want to do it. We lend it to outsiders as well to use that facility. Yes, you can do that. Abhishek. Good morning to Kavya and Muthu. And Utthav as well. All of you. Good morning to all of you. which is the least used numerical method among researchers solving differential equations? Well, I can say that what's the most used, I mean, which is, the ones that we have done, but least used numerical method, it's hard for me to say. The one that gives you maximum error, and everything is iterative in terms of solving differential equations. Everything is iterative. And in fact, the lower order things which we have taught during the course, those are least used in some sense. Monte Carlo using Python, go through the equipment error. Do you really want to go through any equipment error? I doubt, because Monte Carlo is it's a stochastic process of calculating, say, an integrals, or you want to do a simulation in order to evolve a system such as a spin system. So there is no real equipment error that needs to be taken into account in the Monte Carlo for these kind of cases. But if you are only talking about if you're only talking about the Monte Carlo just for doing integrations, then also I don't know, I mean, how you can actually do an integration using an equipment. It is always an integration of a function and splitting that into smaller, fragments, and calculate the area of each of the fragments and then integrating it over. So really, you have to tell me a particular situation in which you need an equipment error. Is Abhishek, yes, you can do a simulation of quantum system. You mean, you meant the quantum dynamical system. Yes, there are, quantum Monte Carlo that is there. For bosons, it's not anything different than what you do. It's accepting that you have to treat them as particles, indistinguishable particles. For fermions, there is a problem because when you do a swap of particles, quantum particles which are fermions, you have to make sure that you don't bunch particles more than one particle at a given quantum state, or even at a given point in the lattice if you're doing a real space simulation. And also have to make sure that the probabilities of doing such swaps do not give you any negative contribution. So yes, the quantum Monte Carlo is really something involved. You need to learn that separately, and there's now the Monte Carlo, the molecular dynamics is used for classical systems. So just solving Newton's law kind of equations. I don't know whether people use molecular dynamics to solve Schrodinger equation as well. They could. I am not aware of that. Let me take Muthu's question first. Computation in Python is much easier. Okay, I mean, Python is almost like the way you speak, you write it in this. Fortran has, of course, more syntax, but for larger simulation, Fortran is more useful. Okay. In Taylor series numerical method, the error propagate in this particular fashion that when you do a Taylor series expansion, you usually keep up to a certain number of terms, and which are say the of course the constant term can be neglected, but then the first order derivative, second order derivative, third order derivative, and so on. So we usually, when you are doing a Taylor series expansion of a function near a given point, then you don't want to keep beyond the second order, because that's called as a harmonic approximation. And in that case, your third order, fourth order, they get missed out in your simulation or calculation. So then, these are the ones that you have left out, and the dominant one would be the third derivative in that case. So third derivative onwards you are missing, and third derivative is the most important thing. So that is that's what you miss in Taylor series. Okay. Ask about the errors which are, Raki has asked that it's about the errors which are generated by the computer. So if you keep a single precision which is up to 8 decimal places, of course it does it does a mistake of rounding it off at the 8th decimal place or at the 16th decimal place. If your result asked for is result demands an excessive precision, then of course your that is something that the computers miss. And sometimes derivatives in computers are quite risky, as has been told, is that because you have a denominator which tends to 0, and something getting divided by 0, that thing tends to blow up. So if you make this h, which is there in the denominator of a derivative, if that is exceedingly small, then there is a problem of blowing up or singularity happening, and in which case there could be a problem. There are other things which computers cannot handle very well. If you wanted to add a number of numbers, say for example, which are widely different, if there are 10 to the power minus 5 and 10 to the power 5, and there are a string of numbers of this kind, and if you want the computer to add that, it really misses out the 10 to the power minus 5, and so it does not do a good estimation of that. Simulation methods. MATLAB. Do we need other simulation methods to learn apart from MATLAB for scientific work? See, MATLAB doesn't do a simulation. MATLAB, what it will do is that it will solve an equation for you, or will try to give you a numerical value of some number and so on. If you want a MATLAB to do a little bit of, which you can do a few steps of simulation, or few iterations of simulations, you can do that. But there are many simulation methods which MATLAB can handle, or Mathematica can handle, and so on. But they are not particularly good for, these softwares are not particularly good for simulation. They are good for other kinds of things. Numerical solution, analytic solution, interpolation, and various other things, plotting of graphs, etc. So these are good for that. But particularly for simulations, you don't get very good results. The thing is that because there is a code that is inbuilt into it, and you have no control on the code. So if you want to do a change in the code for doing a simulation, then you'll be in for a trouble. So that's why the other kinds of numerical methods, MATLAB and Mathematica, etc., would be good. Yes, of course, you're correct. If you have singular matrices or as close to singular, then finding an inverse is very difficult. Correct, you are. Because when you try to find an inverse, you need to divide it by the determinant. If the determinant vanishes, then it becomes very difficult. You're correct, absolutely. Thank you, S.K. Mishra. So, seems there are no more questions, then we'll wind up in some time. If there are questions, please do ask. So finite difference method can be used particle in a box. So basically what you want to do is that the particle in a box is minus h square by 2m d2 psi dx square equal to e psi. So you calculate the second derivative using the finite difference method. So you can do a backward difference, you can do a forward difference, you can do a 5-point difference, you can do a 7-point difference, and so on. The more you increase this difference methods, then the more accurate it's going to be. Yes. Um, software. See, MATLAB is a software, and Python is a programming language. So for numerical methods, I would say you use Python and do a coding of all this. How to choose initial random values efficiently. This is quite tricky. Okay, Abhishek, this is quite tricky. I mean, you have to have an idea of um, the the problem and where could the solution lie. In the vicinity of that, you have to choose. But there is something that I have not discussed, is called as a Broyden method. So when you choose it for the first time, the next time when you go to, in order to have convergence, you can have a much better convergence if you don't discard the old value completely and take a superposition of values which you have got at the present iteration, and a part also from the last iterations. Okay, this is called as a Broyden method, and the mixing can be done by doing an optimization problem. But there is no real answer that how efficiently the random values can be chosen so that the convergence. What you can do is that you can do a background check of the function that you want to solve and see where it has a zero or whatever property you're looking for. Plot it and see that where can it have a zero, and then exactly the numerical method, and then you can fit or rather put that, plug in that value into this problem. Yes. Akileshwar, I'm doing research on drone CFD using TDMA, other numerical methods. Can the results from these methods is sufficient to publish? Yes, of course, they are sufficient to publish a paper. Uh, yes, of course. I mean, in the sense that all these CFD would require you to write code. Suppose you are solving Navier-Stokes equation um, or other equations and so on. And then these are the numerical methods that you use. I mean, there are lots of softwares nowadays which use the same numerical method. And yes, please, it's good enough for you to publish a paper. Yes. Recent trends, of course, recent trend is of course going towards machine learning and artificial intelligence. So, I mean, is almost the understanding of numerical methods is over. That whatever that present data that you have could predict, the behavior. Now you want to ask the question that how can this data that are available to me can be used for predicting future results or results that we don't know or results that can be used for future things, either for future or for extending the domain of its applications and so on. So these are something that we if we calculate noise in dynamical system, they say to a certain extent, yes, noise in a dynamical system is really an artifact of the error, and when you know how to calculate the noise, then the error is yes. Other than the error that comes from various things such as round off, etc., or some propagating error. But yes, the noise gives you an idea. I would not be able to elaborate it at this point, but yes, the noise has some uh, information about the error. Yes, when you know how to do it, then you also know what the error is. Not in every case, I believe, um, but yes, in most of the cases, yes. Please ask your questions now, because if there are no questions, then we'll wind up. So, if there are no more questions in the next 2 minutes, then we'll close it. Please ask me now if you have questions. Of course, there will be another session in which yes, for the initial random value problem, can we turn into an optimization problem when the error is taken as a loss function and optimized with respect to initial? Good question. In fact, yes, this is a particular a thing that we have not really discussed much. But yes, if you do an optimization of the problem and then the error is taken as a loss function in every step of the iteration, then you can do that. Yes, that's right. Abhishek, I usually take physics courses, so I have a course on condensed matter physics lined up, also course on possibly quantum Hall effect lined up, and various other things. So this is a course which is generally for people who are interested in numerical methods and the simulation techniques. But I otherwise I'm from the physics department, so I'll have a number of courses are being lined up. A condensed matter course just in the next semester, I believe, if I'm not wrong. Thank you, Arvind. Yes, you keep an eye on the SK Mishra. Please keep an eye on the NPTEL website. They will advertise the starting. It is right now these things are going on for this advanced condensed matter physics course. But that oh, okay, quantum Hall effect. Yes, quantum Hall effect will start in some time. It is right at the top of the priority of it is there. So quantum Hall effect, if you're interested in, please keep an eye on this. It will be an elaborate course on quantum Hall effect. Recent areas of research, Padma, I mean, as I said that most of the techniques are exhausted and people know them very well. And fortunately or unfortunately, the softwares or have come, computing platforms have come, which these softwares, they perform very well some of the numerical methods that we have discussed. So it is really going towards the machine learning areas where there's a large requirement of accumulation of data and trying to make a prediction of the data. Okay. But of course, there's always, it's an open field and people always think of doing, I mean, inventing methods of solution of a particular problem using numerical methods, using computers, using numbers, using iteration scheme and so on. And every time there is an iteration scheme that is developed, there are follow-up developments which make the iteration to be better, how the updation of different parameters can be done. All these things are constantly going on. Okay. But if you're really interested, then it is just the machine learning and artificial intelligence where it is heading towards. You too, stay safe. Thank you. Thanks a lot. Abhishek. Thank you, Padma Joshi. Thank you, SK Mishra. Arsha Nosat, thank you very much. Thank you, Arvind. Prashun Kumar, that's a difficult question. So graduate studies in physics, you need to be very disciplined, and you need to be very attentive in your classes during your graduate days. I mean, classes means you're probably talking about PhD. If you're talking about PhD, then it is very important that initially follow very religiously what your supervisor says, because he has something in mind, and not everything can be told to the student exactly. One doesn't know what you're looking for. And when you come in tune with the supervisor in terms of thinking, in terms of resonating with him, it becomes much easier later on. Okay, so any field of research is good. It is equally interesting. Any field. I would not say that this particular field is more interesting than the other. Anything is important and interesting, provided you take enough interest in that and think that this is what you're going to do your PhD on. I believe you said about graduate studies. When you said graduate, I meant PhD. So that way. SK Mishra, yes, machine learning and artificial intelligence, many fields, cold atoms, optical lattices, Ising model, then practical problems such as I said about this problem on carbon emission and power grid. So a power grid of India has a very large amount of data, and they are extremely complex networks. So whether there's going to be a grid failure, or there is going to be a sort of this thing that can be predicted using artificial intelligence, given the data of a number of years, so to say. There are, it's used in gravitation, in cosmology, in astroparticle physics, condensed matter physics, everything. Yes, it's very large. Artificial intelligence has very large applications in physics. Shivam Pandey, if you want to use numerical method and FEM, yes, numerical method. As I said, the numerical method forms the basis of machine learning. Okay, you need to know numerical methods first in order to get into machine learning. Yes, you can do that. Thank you. Thank you, SK Mishra. Thank you, Muthu. Oh, you meant master's program. Okay, so yeah, all right, yeah. So the graduate word is used in United States with as a PhD. Yes, the master's program. That's what I started with. You need to be very disciplined with regard to your courses. There should be no pileup of ununderstood things, concepts, etc., or topics in your this thing in your MSc program. So you be up to date with all whatever is happening in the class. I mean, I of course understand that most of you may not have regular classes because of the ongoing pandemic, which is very unfortunate, really unfortunate in terms of learning. I don't know what your university or your institute has done arrangements for your learning. Here we are, of course, teaching usual way. And yes, I mean, in the sense that do more application oriented, that is problem oriented things which really tests your understanding. In IITs, that's what we do. We all give problems which are based on understanding of concepts and never something that you need to memorize or write from, I mean, from your rote learning. But yes, you have to be really, disciplined, up to date, and not let many of the concepts pile up over time. Get them cleared at the earliest, either from your peers or from your teacher, from internet, from everything that is there. So that way, you'll have a good understanding of the subject and can go along with the rest of the class or with the teacher at least. Okay. Multiple choice, there is no good answer that how can you be strong. Multiple choice answer, it requires you to work out the things, and if you want to eliminate, then you're looking for a shorter route, which is never a good thing. Sort of, I feel that you should not take a shortcut route to answer multiple choice, multiple type of multiple choice type of questions. In fact, if you try to do that, you will land up in a loop which will not let you learn extensively. Pula Roy, yes, good morning. Um, I mean, all professors are good, but theoretical physics, of course, you can speak to Dibyendu Das or Anirban Sai. Um, there may be others also. Prabhakar B. Singh. Bhola Roy, I wouldn't know how to download a book. Sorry. So it looks like that, yeah, Hani Sharma, thank you. Looks like that there are no questions on the topic, on the subject. There are other questions, of course, which I didn't mind answering, but since we are running out of time, just ask me something very related to the topic, uh, and then we'll carry it on for maybe a few minutes and then we'll stop otherwise. So if there are no more questions, we are going to close now. You could continue to ask questions if there are more of them in your portal. You'll be happy to answer them.